Good morning, students. So, in the previous class, we discussed about applications of the Kirchhoff law. That means how to apply the Kirchhoff law, and with the help of Kirchhoff law, what we can solve. Like we can find the current in the different branches. So, we solve some problems based on that, and we can find the potential difference between the any two points in the circuit. So, by assuming some imaginary cell or between applying directly between from one point to other point. And finally, we also discussed that we can also find effective resistance in the circuit, right? So we can also find the equivalent resistance in that circuit. And now, basing on that, I will explain one more problem. That means, if whenever such junctions are given, with the help of that, we can find potential or current flowing in the different branches also. So after that, I will explain that Wheatstone bridge. So in this, so now what I am saying is, suppose here the circuit is given like this, a branch of a circuit. So three resistors are joining here. So now these are the points here. Now let us see here, I am taking this as this is point A having some potential of 20 volts, and this is point B having some potential of 10 volts, and this is a point C having some potential of say 5 volts. And now this resistance is suppose I am taking this 5 ohm, and this resistance is 20 ohm, and this resistance I am taking it as some 15 ohm, right? And so now here our question is we need to, this is the junction O here, and so now we need to find the potential at the point O and current flowing through the 15 ohm resistance. So write it as the next problem in that. So this is also just application of the Kirchhoff law only. With the help of Kirchhoff law, you can solve it easily. So a branch of a circuit is shown in figure. A branch of a circuit is shown in figure. Then find potential at the point O. Potential at the point O. And also find current flowing through the 15 ohm resistor. And also find current flowing through the 15 ohm resistor. So now here I am assuming some currents here. We know whenever you are applying the Kirchhoff law, first we assume some current distribution in the circuit, right? So that is, and we also know that is your choice. You can assume current in any way, that means flowing in any direction you can assume. The only thing is, it should obey the Kirchhoff first law at any junction. Suppose here I am taking this, this is the current I is flowing along this direction I am assuming here, right? And so next here let us consider some current I1 is flowing along this direction and some other current I2 is flowing along this direction. Okay. And so now here this I1 and I2 may be opposite direction actually. So now we are assuming like this, because here you don't know actually here. If this is less than the 10 volts if you are getting, for example here, less than 10 volts if you are getting, then current will flow from high potential to low potential like this. So if it is like that, then finally you will get that I1 value with the negative sign. So that finally we can get that conclusion there. So we know already, we solved already some problems based on this. We can assume current in any direction, right? And so now just I am writing this Kirchhoff first law here. So now by KCL, that means Kirchhoff current law or Kirchhoff junction law, at junction O. So if I apply this Kirchhoff junction law at that junction, so I can write this as I is equal to I1 plus I2 we can write. So now just that I value I am substituting from here. So that means you know the potential, here I am assuming this potential at this point as V0. Potential at that point, let it be V0. This is we are assuming, so we need to find that value there, right? And so now I can write this as now current I, we can write as potential difference. V by R formula I am writing. There V is nothing but potential difference across the resistance, right? So now potential difference across this resistance I can write as, we are assuming this is high potential, so 20 minus V0 we need to write. Got? So then it is 20 minus V0 by R. This is 5. Is it clear what I am writing? Just I am writing I is equal to V by R formula I am applying here. This V means potential difference across the resistance. Potential difference across the resistance means when you are assuming current in this direction, that means we are assuming that this is the higher potential. So 20 minus V naught we need to write. That gives a potential difference across this resistance by its value. And this is equal to, now I1, this one we can write here. So then potential, this current is flowing like this. That means we are assuming this V naught is higher potential. So then it is V naught minus 10 by this resistance is 20 plus I2. I2 means here. So similarly here potential difference is V naught minus 5. So then it will be V naught minus 5 by, here the resistance is 15 ohms, right? So now just we need to simplify this equation here. So if you simplify this equation, then you will get the V naught value. If you know the V naught value, and by substituting V naught values here, either you can calculate I1 or you can calculate I2 or you can calculate that I values. So let us simplify this equation here. So just I am multiplying with that say 60. Then if you multiply with the 60, then 12 into 20 minus V naught is equal to 3 into V naught minus 10 plus 4 into V naught minus 5. That's just it's a simplification only. You can do as you wish. And so here this is 240. So it is 240 minus 12 V naught is equal to 3 V naught minus 30 plus 4 V naught minus 20, right? So let us write all the V naught terms on one side and then let us simplify this equation here. So then it is 3 plus 4, 7, and this value will become plus 12. So then it is totally 19 V naught. So 19 V naught is equal to, so now all the constant terms we need to write here. This is say 30 plus 30 minus 30 and minus 20, 50, and so then it is 290. And from this we can write this V naught value as 90 by 19 volts. So that is our V naught value, potential at that junction. And so now by using that, now we can find the current here, right? So then this value to identify whether these directions of current or correct or not, what we are assuming. So let us further simplify this. Then this value, I think approximately, if you define this, so I can say it as 15.26 volts. Let us consider that. That means you will get some other values. So I am taking up to that second decimal. And so now here 15.26 volts means then it is greater than the 10 volts. So right, then this I1 current will flow in the same direction only. And similarly it is greater than this 5 volts also, and so this assumption is also correct. That means the current directions what we are assuming is correct only. If you substitute in that I1, I2, I3 expressions, then you will get those values there. That means now I can substitute, like if you want to find this I1 value. So I1 value means now we can substitute like V naught minus 10 by 20. So that is nothing but 15.26 minus 10 by 20. So then it is 5.26 by 20 amperes. And similarly now you can find this I2 value also. This I2 is nothing but actual our question, current for the 15 ohms. So then this is 15.26 minus this voltage is 5 by this resistance is 15. And so this I2 value will be 10.26 by 15 we can write amperes. So if you want, you can further simplify these values here. And now if you are adding that I1 and I2 values, then you will get this total current I here. That means if you want to calculate, then this I is equal to I1 plus I2 you can write. You can add those two values there, right? So that is a way of solving such a type of circuits. That means just we apply the Kirchhoff first law. I is equal to I1 plus I2, and then we are applying the just this V, I is nothing but we can write it as delta V by R, that means potential difference across that resistance by R, right? And so now in this circuit, sometimes they include the cells also. That means they will give the potential difference and they will give these cells also. Now let us see how to solve such a type of questions then. So now let us see this circuit like this is resistance is there and here one cell is connected like this, and here I am considering another cell is connected here. So now that means in addition to the previous problem, just we are including the cells also here, right? So now I am taking this, this is again point A and this is point B and this is point C and this is say 20 volts and this is 10 volts and say point C is 5 volts. And so now let us take this EMFs as I am giving like this is 30 volts and this is 10 volts and this is 5 volts and this resistance is 10 ohm, 20 ohm and this is 30 ohm and this is the point O here. So here also same, we need to find the potential of that point O and current through the different resistors we need to write. So just write that question. In the circuit shown in figure, find potential of the junction O, and current flowing through the different resistors. So then here also like our previous problem, here also I am assuming some current directions here. You can assume, as I said, you can assume in any direction. Suppose here also I am assuming like current is flowing like this. This is our assumption only. Finally it may be direction may be wrong. So then just I am assuming here current is flowing like this. So similar to our previous assumption I am taking here currents, right? So then I1, this is I and I1 and I2 is flowing like this. Irrespective of the polarities or irrespective of the potentials, I am taking like this. Now again by Kirchhoff current law at junction O. So then that you can write this as, so just I can write similar to our previous, I is equal to I1 plus I2. Let's suppose this is equation 1. And so now here similar to our previous problem, you can't substitute our I1, I2 values directly here because in between that the resistors and cells are also there. So when you can't write directly the delta V by R value here, right? So for that what we can do is, you can apply the Kirchhoff law here. You can apply Kirchhoff law from here and this is V0, let us assume here again. So then you can write the Kirchhoff law starting from one point to another point here. We know how to apply between a points, between 2 points here. And so then I am writing this by KVL, Kirchhoff voltage law, along AOB. That means that points I am taking here, AOB. And so then that we can write it as, I am writing along that AOB direction I am writing here, Kirchhoff voltage law. So then between 2 points we discussed already, VA minus IR. So that means minus 10 into I because we are traveling in the direction of current. So here we need to write minus 30 because we are traveling from positive terminal to negative terminal. And here it is V0 and directly I can move to this point here because here nothing is there, we are applying from here to here. And so then here it is minus negative terminal to positive terminal we are traveling here, so plus 10 you will get. And the same current I1 we are assuming here, we are traveling in the direction of current. So then 20 I1 minus VB is equal to 0, right? So just we are applying Kirchhoff law from here to here. When you are applying from here to here, no need of including this V naught here. V naught doesn't include. In Kirchhoff law, we write potentials when you are traveling from one point, whenever resistance or cells are there. So starting from here, you can apply up to here, right? Or you can also do one thing. The another thing what we can do is, you can apply between from here to here. Then you will get I value, expression for I you can calculate, and similarly from here to here you can apply. Then you will get I1 value, and similarly from here to here you can apply. Then you will get I2 value. Then you can substitute I1, I2, I3 in that equation. So like that also we can solve. That is your choice. That means if you are solving like that, then it will be similar to that of our previous problem. If you are solving like this, then you will get equations in terms of I1, I2, I3 and I, and then we need to solve those equations. Then by solving those equations, you will get those I1, I2 and I values first. From that you can calculate our V naught value. Is it clear? That means what I am saying, in this method, when you are writing from here to here, next we consider another 2 points like A to C or B to C you may consider. So you will get another 2 equations. That means another one more equation. By solving equation 1 and this equation and that equation, first you will get I1, I2 and I values. Once if you know the I1, I2 and I values, you can calculate this V naught value easily. Or instead of this applying this from A to O, if you are applying directly from this A to O and O to B and similarly from O to C, then you will get directly V naught value first. So then from that V naught value you can calculate this I value. I think this method you know, you can solve easily. So just I will explain here how to see this. I will write the equation, do the calculation by yourself. This V naught VA value is given as 20 minus 10I, I minus 30 plus 10 minus 20 I1, then VB value we can take it as minus 10 is equal to 0. So now let us simplify this equation here. So then this minus 10 and plus 10 minus 10 you can cancel, and here minus 10 you will get. So then this equation I can write this as minus 10I minus 20I1 minus 10 is equal to 0, right? And so that this equation we can write as, you can substitute this I means I1 and I2, I1 plus I2 you can substitute here. So that I can write this as minus 10 of I1 plus I2 minus 20 I1 is equal to 10. You can cancel that 10, then you can simplify this I1 and I2. Minus 3I1 minus I2 is equal to 1. So this is equation 2. Is it clear? We are dividing with the 10 and then we are simplifying this. Minus I1 and minus 2I1 is there, minus 3I1. So that is our equation 2. Next, similarly apply the Kirchhoff law KVL from one point to the another point. Like you may consider AOC or BOC also can consider here. So just I am writing like by KVL along AOC. That means between that points I am applying here. So then you can write directly here. I am directly substituting the numericals also, starting from here, similar to this. 20, that means potential at point A, minus IR, that means minus 10 I minus 30, and next here. After this, next we are traveling along this. We are traveling in the direction of current here. So minus 30 I2, and then here it is 5. And that 5 we are traveling from positive terminal to negative terminal. So it is minus 5. We need to write minus 5, and finally it is minus 5. Potential of that point C. So that is equal to 0. You can simplify this. So then it is 10 minus 10 I means again I am writing I1 plus I2 minus 30 I2, right? So then it is minus 20 you will get. That means it is minus 40 and then plus 20. So minus 20 you will get is equal to 0. And so then again you can divide with the 10 and you can write this equation as minus I1 minus 4I2 is equal to 2. This is say equation 3. That means now by solving these equations, then you will get I1, I2 and I values you can calculate from that. So by substituting those values, by writing those value again from O to A, you can write the Kirchhoff law equation, then finally you can find the V0 value. So let us simplify this. I am multiplying this equation with 4 and I am subtracting that equations there, right? And that means what I am writing is equation 2 into 4 minus equation 3. That means I am doing the simplification like this. So let us multiply this equation with the 4. So then minus 12 I1 minus 4 I2 is equal to 4. So just we multiplied this equation with the 4. The minus of this value we need to write. So then it is minus I1 minus 4 I2 is equal to 2. We are subtracting these equations here. So this is plus and this is plus and this is also plus, minus you will get. And so then this value you can cancel here I2 value, then this value is minus 11 I1 is equal to 2 you will get. Therefore I1 is equal to minus 2 by 11 amperes. And so now you can observe here we are getting this negative sign here. I1 value we are getting as negative sign. So negative sign means I1 is flowing in opposite direction here. So I1 we are assuming flowing like this, now actually it is flowing in opposite direction. That is our conclusion from that, right? And next similarly you can, by substituting that I1 value in this equation, you can calculate that I2 values there. So from equation 2 I am writing like I2 is equal to, I am writing I2 that side, minus 3I1 minus 1, right? And so then this value we can write it as minus 3 into I1 value we can substitute here, minus 2 by 11 minus 1. And so then it is 6 by 11 minus 1, so which is minus 5 by 11. So therefore this is our I2 value here. I2 value is minus 5 by 11 amperes. Got it? So then I2 value, now from this I value we can write here, I is equal to I1 plus I2 you can write. So which is minus 2 by 11 minus 5 by 11. So minus 7 by 11 amperes. So all currents are opposite to our assumed direction here. So right, that is our final conclusion. So that is a advantage in that applying the Kirchhoff law here. There is no any confusion while applying the Kirchhoff law here. Just if you apply that signs properly, then you will get that. You can assume the current in any directions there. And next here, this is I1, I2, I3 values, that means I values. Now our next question is to find the potential of that point O. So can you say how to find the potential of that point O? So for that simply, now we should include the V0 value here, potential of that point O. Then simply what you can consider is you can apply the Kirchhoff law from here to here, A to O, right? Now I will apply that Kirchhoff law here. So let us see. So now by KVL from A to O. So only from starting from A and until this point O we are writing here. So directly I am substituting these values. 20 minus I into 10 or 10I minus 30 minus V0 is equal to 0. Right? And actually I said another method in the beginning. So that is nothing but this one only. First let us calculate this V0 value from this. And so then actually from this I can write. So V0 is equal to, from this, minus 10I and minus 30, right? Just this V0, minus 10 you will get, minus 30 and minus 20, so this is just minus 10. So right, just this V0 value I am writing this side, then it is minus 10 and minus 10I already there. Minus 10I means you can substitute this value here. V0 is equal to minus 10 into I is nothing but minus 7 by 11 into minus 10. So this is minus of minus plus you will get. So that means here this is 70 minus 110 by 11 volts. So this is V0 is nothing but minus 40 by 11 volts you will get. So that is the potential of that point V naught. So like that we need to find here when cells are also included in that. That means when cells are not there, simply you can say problem will be very easy. Just with the help of that Kirchhoff first law you can solve the problem. And whereas when the cells are included like this, then definitely some calculation will be included in this. So then that is a way of solving that. So in the beginning I said another method. The another method is nothing but instead of applying this Kirchhoff law, that is, so in this method you need to identify here, first we calculate I1, I2 and I values, right? Then from that we calculate the V value. The another method is nothing but first you will get the V naught value and from that you can calculate this I1, I2 and I values there. So to find that V naught value, just we need to find the I1 and I2 values like similar to our previous problem, and we need to substitute those values in this equation. So let us see how to find I1 and I2 values. Just by using the same equation, right? I am taking the same equation here. Then you can write this expression for I. Now this problem is over. I am saying the another method. Another method means first we calculate V naught value, then you will get I1, I2, I3 values, right? And so now here I am taking this, from this equation I can write this as 10I is equal to minus 10 minus V naught. So I is equal to minus of 10 plus V naught by 10, right? Or you can further you can write this as minus 1 plus minus 1 minus V naught by 10 you may write. So then this is our I expression. Next similarly you can find I1 value by applying Kirchhoff law between O and B. So only applying between O and C and between O and B, like that you can calculate the I1 and I2 values also here, right? Now simply for example if you are writing from O to C, now Kirchhoff law we are applying from O to C like this, then you will get I2 value. Similarly if you apply from O to B, then you will get I1 value. So now I am applying from O to C. If you are writing from O to C, V naught minus, so this is 30 I2 minus 30 I2 and minus 5, and this is also minus 5 here. This is equal to 0, right? So therefore I can write this as 30 I2 is equal to V naught minus 10. So therefore this I2 is equal to V naught minus 10 by 30, right? And then now I similarly apply between from O to B. So by KVL along OB. So V naught plus 10 minus 20 I2 I1 minus 10 is equal to 0, right? So directly I am applying here from O to B. And so now from this again write 20 I1 is equal to, so then minus 10 and plus 10 will be cancelled here. So V naught, right? And so then this is nothing but I1 is equal to V naught by 20 you will get. This is our I1 value. Now we can substitute this I1, I2 and I values in the above equation 1 here, right? So this is I1, I2 and I value. Substitute these values here. Then you will get V naught value by solving that. Got it? And by finding the V naught value, if you know the V naught value, then you can substitute those V naught values in these equations. So from that you can find this currents I1, I2 and I3 values. So that is a reverse process there. First we will calculate I1, I2 values and then we calculate this V naught values there. So that is either you can solve like this. Is a further calculation is clear what I am saying? We substitute this I1, I2 and I values in this equation. So then you can observe that then only variable will be V naught. So then you will get V naught value. So once V naught value we know, then we can substitute here in these equations, then you will get I1, I2 and I values you can calculate there, right? So that is a way of solving the equations here. So either you can find current values first or potential values first. So that is in case of such a junctions here, when such a junctions are given, you can calculate or you can apply the Kirchhoff law like this. So now next, before going to that Kirchhoff, that means before going to this circuit analysis, I will explain the Wheatstone bridge. Because actually Wheatstone bridge we will discuss in the measuring instruments while we are discussing about the measuring instruments, but I will explain here itself, because with the help of that Wheatstone bridge also we can solve some of the circuits, complicated circuits easily with the help of that Wheatstone bridge, right? And so now let us see about this Wheatstone bridge. So Wheatstone bridge. So bridge means it is not ordinary bridge. So here bridge, Wheatstone bridge in the sense simply it is a device used to find the resistance. So generally we find the resistance with the help of this device, or you can also compare the two resistors. Like here generally 4 resistors will be involved in that circuit majorly. So out of that 4 resistor, if you know the three of them, you can find the fourth one, and that means unknown resistance we can find. If 2 of them are known, then we can compare the remaining 2. That means we are comparing means we can find the ratio, like R1 by R2 is equal to how much, we can compare like this. So those are the general applications, but actually with the help of this you can also find the how much strain is produced in this in the material, and so that is also to be strain meter. We can use it as a strain meter, and we can also measure the light intensities there. So I will explain how this Wheatstone bridge works to measure the strain, or how it measures the light intensity. So just let us first go to the what is Wheatstone bridge, and what are the conditions for this Wheatstone bridge here. And this Wheatstone bridge is actually the same. The principle of Wheatstone bridge we will discuss in some other applications or other devices like potentiometer and in meter bridge. So that we will discuss later after completion of this circuit analysis. So just I will explain the Wheatstone bridge and what are the conditions for the balanced Wheatstone bridge. And so now here this Wheatstone bridge means generally it consists of 4 resistors here, connected in the form of this quadrilateral. So here a galvanometer is connected here, and this is cell, and here some switch will be there here, and sometimes some external resistance, series resistance are also connected here, which is not important for us. Here sometimes they may connect some resistance also here, and so then that is not required for us. So that is not important. That means that is not included in our circuit. And so now here this resistance is P, and this we consider as Q, and this is R, and this is S, right? And this now here this G is nothing but our Wheatstone bridge, and that means galvanometer. Galvanometer means it is a device used to find the small currents, very small currents we can find, and we will discuss later. It can be converted into ammeter and it can be converted into voltmeter also. That conversions we will discuss later. So that means it is a device used to measure the very small currents, and we can also find the direction of current flow also with the help of this galvanometer, right? And it is a very sensitive device. So generally in the general practical circuits, whenever you are using the galvanometer, we connect a high resistance box in series with this. So that means here some high resistance box will be included in this. So then HR, high resistance box. That is because, as I said, it is a very sensitive device. Sensitive device means it is generally designed to measure small currents only, very small currents of microamperes like that. And so then when large current is flowing to the device will get damaged. So to protect that, so we connect a high resistance. High resistance in the sense of order kilo ohms we connect like this, or mega ohms we connect such a high resistance here, right? So then that is the general arrangement of the circuit here. So PQRS, those are 4 resistors. 4 resistors connected in the form of a quadrilateral like this. And so between 2 junctions we are connecting this galvanometer here. So this is, I am taking these junctions as A, B, C, D. So between 2 junctions like B and D, we are connecting a galvanometer, and between 2 opposite junctions, that means A and C, we are connecting a cell here, right? Let's suppose this V is the voltage of the solar, EMF of that cell, let us consider. And so now here, so that is a circuit diagram, standard circuit diagram or the basic circuit diagram for this Wheatstone bridge, right? And so now in this PQRS, those are resistors. That means the value of that resistance also is indicated by that PQ only. That means here resistance is there. Suppose if you are taking this as 100 ohms for example, then P value is equal to 100, right? 100 ohms. Similarly, for example, if it is some 500 ohms, then Q value is you need to take it as 500 ohms. So that is the meaning of that PQRS. So those are the values of those particular resistors. So we call them as PQRS. That means P resistor, Q resistor, R and S, right? So as I said, so this now this circuit is used to find the unknown resistance. So out of these four resistors here, so here out of these four resistors, if three of them are known to us, then we can find the fourth one, right? Out of the PQRS, if three of them are known, then we can find the fourth value. Or if two of them are known, then we can compare the other two resistors here. So in addition to that, here this G, that the G indicates both galvanometer as well as it indicates the internal resistance of this galvanometer. So galvanometer means it is a device. So any device will possess some internal resistance, right? So that internal resistance of that device is nothing. G itself will represent internal resistance also. So remember that. G is a indication of it is a galvanometer. So this device is a galvanometer. So it is a galvanometer, and it also that the G indicates the internal resistance of this galvanometer. That capital G indicates the internal resistance of this galvanometer, and HR is a high resistance. So then when you are reaching the balancing condition, we remove the high resistance box there. So I will explain what is the balancing condition now, right? So just to mention that Wheatstone bridge is a device. Wheatstone bridge is a device used to find unknown resistance or resistivity of given material. Resistivity of the given material. It consists of four resistors PQRS. It consists of four resistors PQRS connected in the form of the quadrilateral. As shown in the figure. Between two junctions, we connect a galvanometer G and a high resistance box in series with it. And between two other junctions, that means diagonal opposite junctions, we connect a cell of EMF say V. A cell of EMF V. Here G also represents capital G. Also represents internal resistance of the galvanometer. So in any circuit, whenever you are connecting a galvanometer in series with it, high resistance box will be there, whether it is mentioned in the circuit or not mentioned in the circuit. So practically we connect a high resistance box in series with it, and we remove that high resistance when you are reaching this very small currents. And so now here just by taking the current distribution, we apply the Kirchhoff laws here. And so now here I am taking this total current is I here, and some current say I1 is flowing here and I2 is flowing here, right? And so now here in BD, actually we don't know whether current is flowing from B to D or D to B. So I am assuming, because we know in Kirchhoff law we can assume the current in any direction. So from B to D I am assuming here, and so then here this current you can say like some current is just I am applying the Kirchhoff law junction law directly. I am writing here I1 is reaching this junction, out of that Ig is flowing along this direction. So then the current in this direction we can write as I1 minus Ig I can write, right? Directly applied the Kirchhoff law and I am taking that. And similarly let us write here current along in this direction, we can write this as I2 is flowing like this, then this Ig is reaching the junction. So both are reaching the junctions. So I can consider like I2 plus Ig you can consider here. So that the total current I1 plus I2 you will get, which is I, that flows out of that junctions there, right? So it is the current distribution in this. And so now let us apply this Kirchhoff law and let us write the equations here, right? So first I am applying like between these two junctions I am applying here. That means for this loop I am applying here Kirchhoff law for this loop. So in this loop I am applying here in this direction. So by KVL for loop AB DA, right? So for this loop I am applying the Kirchhoff law here. So let us write the equations now. So minus I1 into P, and next here, as I said, G is the resistance of this galvanometer we need to consider here. So then you can write this as Ig into G, and next we are traveling from here to here. So that I can write this as plus I2 into R. So this is equal to 0. No source is there in that loop. And so now this I can write this as I1 into P plus Ig into G is equal to I2 into R. Suppose this is equation 1, right? And then next, you may consider the other loop here. Suppose I am taking this loop and let us apply the Kirchhoff law again in the same direction, like in clockwise sense I am applying here, right? And so now there I can write this as, now just apply the Kirchhoff law for this. So by KVL for loop BCDB. So that means for this loop we are applying here. So for that loop if we are applying, then let us write the Kirchhoff law minus I1 minus I2 into G. Next here plus I2 plus Ig into S. Next we are traveling like this, plus Ig into G is equal to 0. So now this equation again I can write this as I1 minus I2 into Q is equal to, so I am writing here Ig into G, so this is I1 minus Ig plus I2 plus Ig into S. Suppose that this is equation 2, right? And so now here we write, now these are the general equations now. Now here we mention that when the bridge is said to be balanced, Wheatstone bridge is said to be balanced. So now the Wheatstone bridge is said to be balanced when Ig value will become 0, right? That means, or I can say that here we adjust the values of this P and Q such that the current flowing through this galvanometer will become 0. That means if you are adjusting these values, P and Q values or R and S values, that means resistance in that circuits, we can get a situation where this Ig value will become 0. That means we can observe in the reading of this galvanometer here it shows 0. And now when you are reaching Ig value very close to 0, that means almost like 1 milliampere, 2 milliamperes current, or almost if you are reaching the 0, the current goes on decreasing if you are changing some resistance PQ value suitably here. Now when you are almost approaching that 0 value, Ig value as 0, then we remove this high resistance box from the circuit. So the purpose of high resistance box is here to protect the galvanometer from the high currents. When high current is flowing through the galvanometer, then it will get damaged. So to protect it from high currents, we are connecting the high resistance box in series, right? Now, when you are reaching the almost zero, that means already current is reduced here. So to get the values more accurately, we remove this high resistance box. So resistance box in the sense just there will be some plug will be there. If you remove the plug, then automatically then current will be, that means that resistance will be excluded from this. That means no need of removing all the connections. So resistance box will be there. When you are going to the laboratory, you can observe those resistance box. So just here actually in the practically that resistance box will be there like this. That means here some plug point will be there. So one like this plug will be there like this, screw will be there like this, and here in between this some resistance will be there here. The circuit connections will be there like this. So if you are putting that plug here, if you are putting that plug, actually that indicates that now this is a conducting path here, then current will flow directly from one point to other point directly like this, because this plug will makes in contact with this. So directly current will flow like this. When you are removing that plug, that means if you want to short circuit that high resistance, we need to keep that plug, we need to close that plug. If you want to include this resistance, we remove this. If you pull it out, just we can pull it out like this. So just if you are putting it like this, then it will make the contact with the walls here. It will make the contact with the wall. Then it will be short circuited. Current directly flows here. Below this resistance will be there like this. Then no current will flow to the resistance. That means if you want to remove this, just we need to close that plug there. If you want to include the resistance, just we remove this. When we remove this, then circuit will be like this, right? Now there is no chance of flowing current directly here. So current definitely should pass through this resistance. Then here that high resistance value will be there here. So this is nothing but our working of that high resistance box there. Just that box will be there. If you want to include the resistance, we remove the plug so that the current will flow through the resistance and the resistance will be included. That means initially the situation will be like that. That plug will be open, position will be there. If you want to short circuit that means if you want to remove the high resistance, just we close the plug, right? So that is a simple arrangement only. So that means we can remove that high resistance box here. So when you are removing high resistance box, then you can calculate its value more accurately. That means exact value we can calculate there, right? So that is the purpose of this high resistance box. So then whenever later there will be different arrangements will be there, or different meters will be there where we use a galvanometer. So always remember, whenever you are using galvanometer, definitely we will use this high resistance box here. That is the purpose of the high resistance box, to protect the galvanometer from high currents. So because initially suddenly if you switch on the circuit, then suddenly large current may flow through this galvanometer, because we don't know how these resistors are arranged there. So then initially to protect that we need that. So when you are adjusting these values such that current to the galvanometer is 0, then you can remove this high resistance box here. Then we can find those values more accurately there, right? And so now here after this, so now I am saying that current is approaching to 0. So when current approaches to 0 means you can say that the potential of these 2 points must be same. We know there is no current flowing through the circuit when the potential of the 2 points are equal. So that when 2 points of equal potential are connected to by a resistance, then there is no current flowing across that, because potential difference across that resistance will be 0. And so that here no current will flow through this resistance, that means through this galvanometer here. So then we can also say that potential of this B and D will be same. Then no current will flow through the galvanometer. Then the bridge is said to be balanced. So that is the balancing condition of the Wheatstone bridge. So remember that. Balancing condition of the Wheatstone bridge means no current will flow through the galvanometer, because the points A and point B and D will be at same potential. So mention that. So Wheatstone bridge is said to be balanced after this. Wheatstone bridge is said to be balanced when current flowing through the galvanometer is 0. When current flowing through the galvanometer is 0. This is possible when VB is equal to VD. Potential of B is equal to potential of D. So this is the balancing condition for this. So when bridge is balanced, then Ig value is equal to 0, as well as we can also say this Vb is equal to Vd, we can say there. So that is the condition for the balancing Wheatstone bridge. So whenever bridge is balanced, then that is the indication there. So from that what we can say is, when this bridge is in balanced condition, so whether this resistance is there or even if you remove that resistance, there is no change, right? Because no current is flowing in that path. You may even if it is present in the circuit, it doesn't affect any current value. So even if you want, you can remove that, right? So now let us see how these equations changes when you are approaching that such a conditions there, right? So now let us see what the changes takes place in these equations here. Now, so that means I can write this value as I1 into P is equal to I2 into R, right? Suppose this equation I am taking as equation 3. Got it? Just here in this equation 1, Ig value is 0. So this term will become 0. Then I1 into P is equal to, then you will get I2 into R, right? Now similarly from equation 2, from this equation, again let us substitute Ig is equal to 0. So then Ig is equal to 0 means you can substitute here. Then you will get I1 into Q is equal to, this term is also 0 and here also Ig value is 0. Then I2 into S you will get. So then this is equation 4. Now let us take the ratio of that equation 3 and 4. So now let us take equation 3 by equation 4. If you find this ratio, then I1 into P by I1 into Q is equal to I2 into R by I2 into S you will get. So from that what we can write is P by Q is equal to R by S. So that is the most important condition here. P by Q is equal to R by S. That means then when this condition is satisfied, then you can say that the bridge is balanced condition. That means it is a like a reverse if and if only condition here. If this Ig value is 0, then definitely that ratio will be satisfied. P by Q is equal to R by S. So that is a balancing condition for the Wheatstone bridge. That means to check simply, or you can say the reverse also. That means if that ratio is satisfied, then you can say that no current is flowing through this resistance here, right? And so now that condition is said to be the balancing condition there. So when P by Q is equal to R by S, the Wheatstone bridge is said to be balanced. So here mentioned that this is called balanced condition for the Wheatstone bridge. This is called balanced condition for the Wheatstone bridge. So now is it clear what is the balanced condition for the Wheatstone bridge, or what is the basic principle there? Simply no current should flow through the junction from B to D, right? That is nothing but the potential of point B and potential of point D must be same, right? And then for that is possible when you can also say like when P by Q is equal to R by S. When ratio of these two resistors is same as that of the ratio of these two resistors, then automatically no current will flow through this resistance here. So that is a balanced condition here. So that means when some circuit is given and if they are asking like whether the circuit is in balanced condition or not, we just verify that. If that ratio is satisfied, that means we find the P by Q value and we find R by S value. If both are same, then you can say that that the Wheatstone bridge is balanced here. So that is the balancing conditions there, right? And so next here, let us see some other points regarding this Wheatstone bridge here. So therefore mention that that is called Wheatstone bridge. And if Ig is equal to 0, then that condition is satisfied, or if that ratio is satisfied, then Ig will become 0. So mention that the above relation is called balancing condition for Wheatstone bridge. The above relation is called balancing condition for the Wheatstone bridge. When this condition is satisfied, current flowing through the galvanometer will be 0. current flowing through the galvanometer will be 0. Or VB is equal to VD. That means potentials will be same. B and D will be at same potential. And vice versa. That means if Ig is equal to 0, then this condition will be satisfied. That also you can say that vice versa. That means if when Ig, or we can say when Ig is 0, then above condition, that means this P by Q must be equal to R by S, right? And so now let us write some points regarding this Wheatstone bridge here. And so as I said, this Wheatstone bridge is used to find the unknown resistance, right? This is generally used to find the unknown resistance there. Now we can calculate more accurately if all these resistors are same or at least nearly same. If they are nearly same, then sensitivity that this Wheatstone bridge is said to be more sensitive. That means you will get more near values there, or more accurate values. So mention that Wheatstone bridge is said to be more sensitive when all the resistors are equal. When all the resistors are equal. Right? That means you can calculate the unknown value more accurately if three of them are equal. If three of them are equal, and if we are finding this value here, then automatically if galvanometer shows 0 reading, then for the particular value of this P, then P value is said to be more accurate when compared to the any other combinations there, right? Because just to take the ratio to be satisfied, you can take any values. Like for example, here this values I am taking some 10. Let us take 100, and this value let us take 10. And suppose here for this R and S I am taking the ratio like this is 10,000 and this is say 100, right? Now here, 1000. Then this ratio P by Q is equal to, will get 10, and R by S is also will get 10. And so now here, now these values, if you are finding this either P value or Q value by using such an arrangement, then it doesn't give the more accurate value. Some error will be there here. Generally in measurement of any value, error will be there. So that error will be more if all the resistors are different. If all of them are same, for example, then you can calculate those values more accurately there. That means the device is said to be more sensitive. For small changes also it can identify easily. So that there is a point you need to remember there. When all the resistors are equal, the device is more sensitive. And next point. And so now if I interchange the galvanometer, position of the galvanometer and position of the cell, so is there any changes taking place in that balancing condition? So if I interchange the resistance, that means if I interchange the position of this galvanometer and the cell here, interchange in the sense between B and D if I connect the cell, and between A and C if I connect this galvanometer, is there any change in the balancing condition? So I will draw that circuit now. So between these two, what I am saying is between these two, I am connecting a cell here. So some cell will be connected like this, and between these two if I connect the galvanometer. So now the galvanometer is connected like this. That high resistance remaining usual arrangements will be there. If the connections are like this, then is there any change in the balancing condition? So that means actually in this you need to write like this. So previously remember this, our previous part is, so here some resistance is there, and here some resistance is there, and here some resistance, and here also some resistance is there. So this is PQRS we are taking, right? So then this is the position of the galvanometer. For the balancing condition, P by Q must be equal to R by S, right? Now the galvanometer we are connecting between these two here. Between these two junctions we are connecting that galvanometer. Then actually our condition should be P by R must be equal to Q by S. If this condition is satisfied, then in this, similar to that I am saying now, if the galvanometer is connected between, instead of this, if it is connected like this, then that is our condition. If the galvanometer is connected like this, between these two junctions, if it is connected, then ratio of these two resistors must be equal to ratio of these two resistors. So P by R must be equal to Q by S. Then that is the balancing conditions there. Now we can observe that this ratio and this ratio both are same only, right? Just you can rearrange the terms here. Q you can write here and R you can write here, so that there is no change in that equation. So then just we need to write this value here. Actually these two are same only, right? That means if the galvanometer is connected here, then we need to write this condition. Now this condition and that condition both are similar only. There is no change in the balancing condition, right? But sensitivity of the device may change. Sensitivity of the device may change here, because even though ratios are same, some resistance may be smaller and some resistance may be larger resistance you may get there. So mention that, write it as the next point. When we interchange the position of cell and a galvanometer, cell and galvanometer, then there is no change in balancing condition. So just draw this diagram and write this equation here. And that continue that there is no change in balancing condition, but sensitivity of the Wheatstone bridge may change. Sensitivity of the Wheatstone bridge may change. And about this sensitivity and how the error will be, we will discuss in detail when you are discussing the meters, right? And so that means draw this, write this equation and also mention that this is nothing but these two are same only. That means P by Q is nothing but R by S. Either you can mention like this or you can mention like this. Just we are rearranging the terms here. We are writing Q here and RS, R here. Next. So mention that other applications. By using Wheatstone bridge, we can find unknown resistance or resistivity, because once if you know the resistance, if they are asking the resistivity, you can calculate just by using our resistance formula here. R is equal to rho L by A. By using that you can find the resistivity there, if a resistance of the material is known to us, right? Because you can calculate length and area of cross section by using the devices. Like by using scale you can calculate the length of the wire, and by using screw gauge you can calculate the area of cross section, that means radius, and from that area of cross section you can calculate. So that means now from that you can find the resistivity of that material. That means you can also find resistivity of the material. Next, Wheatstone bridge is also used to find strain produced in the wire. So can you say how to find how it finds the strain produced in the wire? Because you know, when you are stretching the wire or when you are compressing the wire, then length and area of cross section of the wire changes, right? When length and area of cross section of the wire is changing, then automatically resistance is also changing. So then just by measuring the change in that resistance, then we can find how much stretched wire in the Wheatstone bridge, and again we find its resistance. So just we can calculate the how much change is there in that resistance of that wire. So just by finding the change in the resistance of wire, we can estimate how much strain is produced in that wire, right? Because we know the relation how the resistance depends on the area of cross section and how it depends on this length of the wires, right? So that is. And similarly, in the beginning I said it is also used to measure the intensity of light. So there are certain resistors whose value will depend on the light intensity. If your suppose if light is exposed to that resistance is exposed to the light, so then resistance of such a materials will changes. So those are said to be LDR, light dependent resistance, LDR. So that means if you are connecting such a LDR here, light dependent resistors, if such a light dependent resistors is connected in one of the part here, one of the arm here, then if you are then we find the resistance of the wire initially. Now some light is allowed to incident on this on this resistance here. Then resistance of the wire changes because light is incidenting. The resistance is a light dependent resistance. If you are increasing the intensity of the light, then automatically the resistance of the wire also changes. So then by finding how much resistance is changing, then we can estimate how much of light energy is incidenting on this. That means like that we can also find the intensity of the light also. So just to mention that also, we can also find intensity of light by connecting light dependent resistors in the Wheatstone bridge. By connecting light dependent resistors in the Wheatstone bridge. And next here there will be some different forms are there. And so now actually here by using this Wheatstone bridge we can solve some circuits here. That means we can find some effective resistance here. So when you are finding this effective resistance, so simply you need to remember here when the bridge is balanced. So like suppose here in the usual standard I am taking this as some galvanometer is present here, right? So now if this Wheatstone bridge is balanced Wheatstone bridge, then what I can say is, then you can remove this resistance here. Whatever this resistance G is there, you can remove that resistance, because when the bridge is balanced, even though that resistance is connected in the circuit, no current is flowing through that, right? That is nothing but our condition for the balanced Wheatstone bridge. That means if that condition is satisfied, for example, in a given circuit, if that condition is satisfied. So like what I am saying is, suppose I am taking this circuit like this. I am taking a circuit similar to that of Wheatstone bridge like this. That means now I am saying how this Wheatstone bridge helps in finding the equivalent resistance or effective resistance. Suppose say here instead of this galvanometer I am taking some resistance, because that galvanometer G also represents some resistance. Like here for example I am taking this is 20 ohms and this is 40 ohms, and let us say this is 4 ohms and this is say 8 ohms and this is say some 10, right? Now is this balanced Wheatstone bridge or not? So just to verify that, now we need to find actually the effective resistance between these two. That is our problem here, for example. Now how to use this balanced Wheatstone bridge condition to solve the effective resistance means, in this just we verify here P by Q is equal to, this is our P and this is Q, right? So P by Q is equal to 20 by 40. So we will get 1 by 2. Then I am writing R by S. This is our R and this is S. So R by S is equal to 4 by 8. So you will get 1 by 2, right? So P by Q is equal to R by S. So that means that given bridge is a balanced Wheatstone bridge. It is in balanced condition only. That means if we connect any battery between A and B, no current flows through this 10 ohm resistor, right? Now our aim is to find the effective resistance between the points A and B. So to find the effective resistance between the points A and B, and when this condition is satisfied, that means if in this circuit for example, what I can say is we can remove this resistance here. We can remove that resistance, because even though that resistance is connected, no current is flowing through them. That we already proved in the previous discussion, like when you are proving the condition for the balanced Wheatstone bridge. So no current will flow through this resistance here. So then you can remove that resistance. So if once this resistance is removed, then you can easily say this 20 and this 40 are in series, and this 4 and 8 are in series. So then both the arrangements are in parallel. That means circuit will convert into simple series and parallel combinations, right? But if that resistance is present, that means if you are considering that if we don't know this balanced Wheatstone bridge, and if this resistance is also there, and if I ask find the effective resistance, for example, if you don't know this balanced condition, then you can't say directly that these two are in series, you can't say, because in middle one more resistance is connected there. So that is the advantage of this Wheatstone bridge here. By knowing the balanced condition of Wheatstone bridge, whenever such arrangement is there, you can first verify that whether the bridge is balanced or not. If it is balanced, then we can remove this resistance here. So if you remove this resistance, right, then circuit will be easy. Then here these two will be in series, so you will get 60, and these two will be in series, so you will get 12. Then 60 and 12 are in parallel, so you can find the effective resistance easily, right? So that is the advantage of this Wheatstone bridge. So whenever such a balanced Wheatstone bridge if you are observing in the given problem, you can remove the resistance connected in the place of the galvanometer. So in the given circuit, this is a standard form. You can't expect all the problems based on the Wheatstone bridge will be given like this only. They may give in different shapes. The same Wheatstone bridge may be there in different shapes. Just it is a combination of 4 resistors only, right? So that means now you need to identify the position of the galvanometer, where the galvanometer is connected in the given Wheatstone bridge. So you need to identify that. And so if the bridge is balanced, you can eliminate the resistance connected in the place of this galvanometer, right?